3, 4. 1, 2, 3, 4. Now this is reacting with HCl. Okay, this will now give me 1, 2, 3, 4, 5. Now my chlorine will come in either year or year. Let me now put it here. So year or year, so I decided to put it here, as the case may be. The rest will have hydrogen, hydrogen, hydrogen. So this is 1, 2, 3. 1, 2, 3. 3-chloropentane. So you have seen in the same kind of compound, it's just based on the positions of the double bond. We'll talk about that in isomerism. You have been able to see that here was 2-chloropentane and now here becomes 3-chloropentane. You must now know that the position of the Cl is dependent on the double bond. You don't put it anywhere else other than the double bond. Anywhere outside the double bond, you are completely out. And your instructor will obviously feel you for that. So you must take note. It is very important. So we can do these reactions over and over and over, as many as we want to do. We continue to get the same thing. So let us advance further and see what else we do. Let's go to isomerism. Isomerism of alkenes. Now, I said isomerism is a phenomenon, a process by which a compound having the same molecular formula but different structural arrangement. Now, in double bonds, we have three types of isomerism. We have the positional isomerism, we have the structural isomerism, and we have the geometric isomerism. All these are exhibited by the double bonded compound. Let us see how. We're going to take some questions in relation to that, but then let's see what is the positional isomerism. Positional isomerism is just the difference in the position of the double bonds. For example, if I have 1, 2, 3, 4, 5, I have my double bond here. This is pentene. 1, 2, 3, 4, 5. That's pentene. Now, another isomer of this can become base. 3, 4, 5. 1, 2, 3, 4, 5. This is 2-pentene. If I have 1, 2, 3, 4, 5, 6, for example, and I put it in the middle, this becomes 3-hexene. 1, 2, 3, 4, 5, 6. It can be here, which is hexene. It can be here 2-hexene. It can be here 3-hexene. So that is what positional isomerism, which is based on the position of the double bonds. So you can do that as many as possible. Now, structural isomerism has to go with the position of the double bond and the structure. Take note, the position of the double bond and the structure give us what? Positional isomerism. Let's take structural isomerism. Let's take an example of that. So I have a compound 1, 2, 3, 4, 5. This is pentene. I want to get an isomer of pentene based on structural framework. I now have 1, 2, 3, 4. I still have my double bond here. And I cut one of these and put it here. This becomes 1, 2, 3-methyl butene. Alright? 3-methyl butene, or but1-ene, if you want to put it that way. So this is it, because this is a structure. It's different from this, obviously. And I can still have another one to be 1, 2, 3, 4. I have my double bond here. Okay, this is 1, 2, 3. And I still have my C here. This is CH3. Don't forget that. So if I come from, this is 2. Alright? So I have 2-methyl but2-ene. Because this is 2-butene. Alright? And my 2, the methyl is in carbon 2. So I have 2-methyl 1, 2. 1, 2, 3, 4. 2-methyl-butene or 2-methyl-2-butene. So this is also a structural isomerism. We choose the structure to be different. Alright? And now the last one is geometric isomerism, which is very peculiar to double bonded compound. Let's see an example of that quickly. I have this. Let me put it this way, and this. Okay. Now, in geometric isomerism, we have two forms of arrangement. We have the cis arrangement and the trans arrangement. Cis arrangement means the supposed substituent or thereabout are arranged in the same manner, in the same side. While trans, they are arranged in the opposite manner. Let me take this, for example. If I want to write this in terms of geometric isomerism, I have my double bond here. These two carbon atoms are having that. I have this and I have this. Now, remember this is CH3. This is 1, 2, 3. One hydrogen here. One hydrogen here. And this is my CH3 here. Now, what is the official name for this? This is 2-butene. Okay? Because the double bond is in the second carbon atom. So it's 2-butene or butuene. Now, because of this position of these, this become what? Trans. Remember, because this CH3 is opposite to this other side, it becomes trans. Alright? This becomes trans 2-butene. Alright? This and this are in opposite direction. So let's see the C so that you will get it right. You will not mistake it. If I want to write this in the cis pattern, I have this. I put my CH3 here, my CH3 here, hydrogen here, hydrogen here. So we see that the position of this is different from this. This one's are in opposite, this one they're in the same side. So this becomes cis. Cis means they're in the same side. Cis 2-butene. We can do this plenty, as many as we want. Let's take a compound that will look a little complex and see how we can arrange it in terms of cis and trans. Okay. Let's CH3 CH2 3 C CH3 sorry CH2 CH3. Now if you look at this is a long somewhat compound. Let me take this one out. This is CH3 here, CH2 in 3 places, CH21, CH22, CH23. I have my C, I have my double bond, I have my C. Okay, I didn't put the hydrogen, sorry, hydrogen here. So there is hydrogen here, there is 1, 2. There is hydrogen here to CH2 and CH3. Now, if I want to position them in a cis and trans manner, this is what I can do. I will come down here. This is my double bond here. These two. And this hydrogen, this is the hydrogen. This is C2H5. This is an ethyl group. I'll come here and put my CH3, 3 of them, CH3, 3 of them, then CH3. So this is one, and this is another hydrogen. So you see that I've been able to arrange it in a trans manner. Alright? and this. I can still arrange this, bring this one up here and put it here in a cis manner. So that is how this thing goes. But what is the name of this compound? You come here, 1, 2, 3. A double bond is in carbon 3, 4, 5, 6, 7, 8. The parent chain is the octane chain. Double bond octane, perhaps. So this is 3. What is it? Name it. Octa 3-ene or 3-octane. 3-octane, sorry. Octa 3-ene or 3-octane because it is 8. So in that form, so if you want to call this, you call it trans 3-octane because it is in the trans form. If I put it in the cis form, you call it 6,3-octane. Now, having said that about this, we now look at what we call optical activity. Now, optical activity is the ability of a compound to rotate a plane polarized light in a dextro manner to the right. We call it the dextro rotatory. To its right, we call it dextro. Now, for a compound to be able to rotate a plane polarized light, it must have what we call the Kira center, otherwise called the Kira carbon. The Kira carbon is that carbon that is having 3 or 4 substituents differently. They are not the same again. So now what are we talking about? We're talking about optical activity. Let's see what we do in terms of optical activity. And all optical activity are able to rotate a plane. They can rotate a plane polarized light to its right, which is dextro. So we have a compound. This is CH3. This is hydrogen. This is CH. Let me put it in front. Then CH3 here. This is bromine. Now, your job is to trace the Kira or carbon. To know the Kira carbon. 1. We say a Kira carbon or the Kira center is that carbon that has 4 different group attached to it. Let's think, this is our Kira carbon. Now, this side is a methyl attached to it. This side is a hydrogen attached to it. This side is a bromine attached to it. And this side is an ethyl attached to it. So the 4 different guys attached to this carbon are different. They are not related in any manner. If I have hydrogen here, this carbon is not Kira. Why? Because it has 2 similar group attached to it. Then all the group attached to the carbon atom must be different. As such, we say that compound is optically active because it means that it has the ability to rotate a plane polarized light when it passes through it. So this is 2-bromobutane. Another one, okay, let us see if we can trace our optical, the Kira compound or the Kira carbon. So you have C2H5 here, I have hydrogen here, I have bromine. Okay, let's call it hydrogen. I have hydrogen, I have hydrogen, I have hydrogen, I have hydrogen, hydrogen, hydrogen. I have hydrogen, hydrogen, hydrogen. From here, which of the carbon is Kira? Okay, we want to know if this whole compound is optically active. Means we must be able to trace one carbon atom that has all the substituents or groups attached to them to it differently. Now, if you look here, look up. If you look into this compound, which one here do we say is optically active? Which one has a Kira center? 2, yeah?
No.
Yeah?
Yes.
Okay, let's look at this. It has an ethyl. It has a hydrogen. It has a propyl. It has a methyl. So this carbon is optically, that is the chiral center. Okay? So it's the chiral word carbon. So therefore, this compound is what? Optically active. That is how you know. What is the name of the compound? 2. Are you sure?
No.
Now, let's know if we are correct. Let me break this down. This ethyl, this is what it means. That is what it means. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. This is become the parent chain, not this. So you must first of all identify your parent chain. So this is how the parent chain goes. This is 1, 2, 3 methylhexane. Alright? You don't just because this is attached to this, you can't just say it's 2-ethyl pentanol. First, identify the longest chain, which is the parent chain, and that is it. Okay, we've talked about that. Let's go to the rules of naming. Rules of naming alkenes. Okay. General procedure for naming alkenes. 1. Select as the parent chain the longest continuous chain. Of course, we did that in the previous one. We must first of all identify the longest continuous chain of carbon atoms, which must include the 2 carbon atoms containing a double bond. In this case, our longest continuous chain must have that carbon that contains the double bond. You cannot take the parent chain or the longest without it having the double bond in it, even if it is longer than the other one. The one that has the double bond should be the one you consider first. Then, name it as that of the corresponding alkane. Example, let's take a particular example here. 1, 2, 3, 4, 5. This is pentene. Okay, let's see more. Alright, in that one, they said, since all the 5 carbon atoms form a continuous chain, its parent name is pentene. Why? Let's take another one. Okay, good. I think I have a nice one here. Now, in this one, if you want to get the longest, this is 1, 2, 3, 4, 5. Let's look up. 1, 2, 3, 4, 5 is the longest. But 1, 2, 3, 4 is our parent chain. Why? Because it contains the double bond. This one does not contain the double bond. So we cannot regard this as the longest, rather this. So the longest possible the parent chain must contain the double bonds. So I have 1, 2, 3, and 4. 2-ethyl butene, because the double bond is in carbon 1, or but 1 in, if you want that. Okay, 2-ethyl, the ethyl is in carbon 2. Butene. Let's move further and so we can name more. Now, assign number 1, 2, 3, which I've done serially to the carbons in the parent chain, such that the first carbon containing the double bond is given the lowest possible number. Yes, regardless of the position of the constituents on the parent chain, like I've illustrated. Now let's take, if the position of the double bond is unaffected when the parent chain is numbered forward or backward from any direction, it is not different. If you name from this right side, you have maybe 2 butane. You name from this side, you have 2 butane. But once that happens, now they say the parent chain is numbered forward or backward. Yes, preference is then given to the position of the substituent, for instance. So you now have to consider the substituent that attached to it and give preference to that. Let's take a particular example here. Okay, I think it's 5. 1, 2, sorry, it's 4. Okay, if I put it here, CH3. Now, the double bond, if I come from here, 1, 2, from here, 1, 2, both sides, this is, the double bond is in carbon 2. But now, since from both sides, it gives me the same, preference should be given to the substituent. The substituent, if I want to consider the substituent, it is in carbon 2. But from here, 1, 2, 3 is in carbon 3. So the preference will be given to the side that has the lowest possible, which is 2. So therefore, 1, 2, 3, 4. This becomes the order of what? Numbering. So this is what? 2-methyl-2-butene or 2-methyl-butyene. Are we good? That is the double bond, so pay attention. When naming a substituted alkene, such substituent will, with its number separated by hyphen, becomes the prefix to the parent name. For instance, let's take another example. Okay, it's just the writing format. Okay, let me write it out. Let me finish. For instance, this a particular example will be taken in this form. I think I've illustrated it before, but let's just take it again so that we'll see what they want. Now, 1, 2, 3, 4. 1, 2, 3, 4. Double bond here. 1, 2. Okay, so since there is a substitution there, substituted alkane, 1, 2, 3, 4 is our parent chain. So what they are telling us is, this is 2-ethyl, 1, 2, 2, 3, 4. 2-ethyl, both 2-ene, or 2-ethyl, 2-butene. The one you like best, you deal with that. Alright, so you must separate them with these hyphens. Use this to separate them. That's what they're trying to tell us. Okay, in the case of further cases, there is no need to specify the position of the double bond, since it must be on the terminal carbon. Like I've told us earlier on, if we have pentene, which means the first carbon atom is in carbon 1, you don't need to tell us 1 pentene, just tell us pentene, we know. The double bond is in the terminal carbon. And so forth and so on. When there are 2 or more double bonds, the parent chain must contain as many double bonds as possible. Even if it is not the longest continuous chain, the number assigned to the position of the double bond must be as low as possible. The word ADI, ATRI is then added to the ending in. In place of in, you add ADI for 2, ATRI 3, ATRA for tetra, ATETRA, and so on. Let's take an example here. Example 8, where are you? Okay. Okay, this is now let us identify Now, that is what they say we should add when we have double bonds, or two double bonds, or triple bond, as the case may be. Now from here, I have 1, 2, 3, 4. I have double bond in carbon 1 if I come from here. I have in carbon 1 if I come from here. So it would have been from any direction, it wouldn't matter. But I'm considering this side as 1 because the ethylene group, ethyl group, is attached to carbon this side. So it gives preference from here, 1, 2. Than coming from here, 1, 2, 3. So I come from here then to say 1, 2, 3, 4. Lowest possible locant, as the rule has commanded. Now, this is the second carbon atom. I have an ethyl. So I have 2 ethyl. Remember that in the place of, instead of butene, they say you should change this to this. Okay. Now, let's see how does that work. Now, this is 2 ethyl buta. Okay. Since they are double, okay, sorry, let me come. 2 ethyl 1, 3, 1, 3. The double bond are in position 1 and 3. 1, 3 butadiene. This is the ADI they say should add. Because di means there are 2. There are 2 diene. Okay? Now, we have, in carbon 1, we have how do you call it? An in group, a double bond, which is in. We have another one, which is another in. So we have 2 ins. So in chemistry, when you have 2, you call it di. So we have diene, 2 ins. So now the dienes are in position 1 and 3. So it becomes 1, 3 diene. But the chain is butane. So they said you should take that. Normally it would have been butene. We replace this with ENE. They say no. When you have double bond, instead of the EN, remove this and put ADI. ADI. So instead of butane, become butadi. Since there are 2. If there are 3, it become butatri. Butatetra. Okay? Butatetraene and so on, if it is ever possible. But it can be 4 tetra. So we have to extend the chain to get that. Alright? And so on and so forth. So that is how the whole stuff keep going. And that is how we got this. So let's take another practical example and see how the di and the tri can work. If I have 1, 2, 3, 4, 5, 6, 7. Double bond, double bond, double bond. So if from here 1, 2, 3, 4, 5. 1, 3, 5. 1, 3, 5. Here is 2, 4, 6, 10, 12. This is 9. So I start from this side. So it's better 1, 2, 3, 4, 5, 6, 7. So now let's see. In this case, 7 is called hep. It's supposed to be hep. Okay? Not supposed, it's hep. Heptene, if it is one double bond. Okay, and so on and so forth. So let's position them. 1, 3, 5.
1, 2. Let's try.
Now, how many? Heptatriene.
Yes.
Okay, that's 7. So 1, 3, 5. Heptatriene. There are 3 in. So the ATRI now comes in because there are 3. The way there are 3, bring ATRI to replace this place, which would have been heptene, ENE. You remove it and put ATRI. So it becomes hepta for 7, buta for 4, penta for 5. Then you bring the in inside. Heptatriene, octatriene. whatever it is. And we're going to see a lot of that. But it's cardinal important if you know how to name them. Okay? Questions like this will always come. A whole question will be like, name the various organic compounds. And you keep strong. If you don't have the basic rules, you're going to miss out. Okay, let's take another interesting one I'm seeing here. It's nice. Now, one, because of bromine is in this side, so this becomes preference comes from here. So I now have this as 1, 2, 3, 4, 5, and 6. Now, 1, 2, 3 bromo, 3 bromo, 1, 3, 5, 1, 2, 3, 4, 5, 6. Instead of hexane, become heza. Heza, there are 3 bonds. Triene. Are we following now? Good. So with that, we continue to move on. It becomes easier. Am I right? Yes. Let's take another one. They say we should give the IUPAC names of the following compound. How do we name this? Let's look at the board. What do you think is the name? The parent chain is 4 for butene, and we have a substituent in carbon 2, so that's 2-methyl butene. Another one. Now I can clean, I guess. Okay. Now again, 1, 2, 1, 2. Because of the substituent being this, I can start from the 1, 2, 3, 4. Am I right? Yeah. This is 2 chloro. 2 chloro what? No. 2 chloro 2 butene. Or 2 chloro 2 in. Alright? Let's take another one. Write the structures and the IUPAC names of the following compounds. I'm going to give us a compound. Let's write the structure and the IUPAC names, alright? Okay. These are condensed structures that we have to expand them. Here is CH3. Here is C. It has its hydrogen bonded to another C. Of course, we should know that, okay, it doesn't give us tetravalent, so it must be double bond here. So this carbon. Now from this carbon, we have CH3, 2 of them. So I have CH3, CH3. 1, 2, 3, 4. So we're good. Now, let's say we should name. If I come from here, the same, 1, 2, 3, 4. So I will always come from here because the substituent is here. So this becomes like 2, right? Yes. So now I have 1, 2, 3, 4. 2 methyl, put 2 in. 2 methyl, put 2 in. Or 2 methyl, 2 butene. Let's take one or two more. All right. quickly. The first C H and there is a Z are attached to it. It's bromo. I move down to the second C, I have one hydrogen. Move down to another C, I have one hydrogen. Of course, I will be double bond here, effectively for 1, 2, 3, 4. 1, 2, 3. Now, to this other side, it comes a CH2. CH2. Then the last one is CH3. There are two CH2, then CH3. So this is it. Now, 1, 2, 3, 4, 5, 6 is what hexane. But the double, we have a bromine in one carbon 1 and a double bond in carbon 2. So 1 bromo, 2 hexane, or 1 bromo has 2 in.